For the function to the right, find the same exact goodness. Party! What's the domain? What's the domain? All reals, it's a polynomial. Part B, notice part B changed a little. We're not going to find an x-intercept. To find an x-intercept of that guy by hand, we would have to know some college algebra, so Eugene can do that for us. Remember that P over Q thing? Yep, exactly. Yeah, so he already blanked that part from his memory. So we're only going to do the y-intercept. So how do you find the y-intercept? Set x equal to 0. Now, I do not know what course compass is going to do to you. I don't know if it's going to force you to find the x-intercept. If it does, good luck. So put in 0 in for x. What do you get? -5. Part C and D is what we did in this class. So what tells you about relative extrema, increase and decrease? The first derivative. What is the first derivative? 4x squared plus 4x plus 1. What is 4x squared plus 4x plus 1 factored? Good, 2x plus 1 quantity squared. Next class, I'm going to strap bombs to everyone. And in 10 seconds, it blows up unless you factor it correctly. The trick is going to know how to tell the bomb that you factored it correctly. So it may just go off regardless. So make sure you get to factor it correctly. So 2x plus 1 quantity squared, that's a polynomial. We don't have to worry about the does not exist portion. But when does it equal 0? -1/2. What do we do with -1/2? Number line. Give me a number to the left of -1/2. -1 to the right. Where are we putting these numbers? To the first derivative. If you put -1 into the first derivative, what do you get? Careful. Which one do you get? What'd you say? You get positive. Yeah. Should be positive. What do you get for 0? Do we have any relative extrema? Well, when the first derivative is positive, the function is increasing. Is it increasing everywhere? Do we have to take out any numbers? No, because the domain's all real. So all we can conclude from part C is increasing everywhere. No relative extrema. Mike, you're giving all these special cases. Why do you hate us? I don't know, but why are you talking like this, class? Part D, what tells you about inflection points and intervals of concavity? The second derivative. What is the second derivative? 8x plus 4. So same deal. See where the derivative equals 0. See where the derivative does not exist. Again, does not exist. We don't have to worry about. Huh. We got x to be -1/2. I wonder why that is. We actually don't learn why in this class, why that is. What do we do with our -1/2? Number line. You can even pick the same test values that we did before. But where are you putting these test values now? Second derivative. So putting in -1 into the second derivative, we get negative. Putting in 0, we get positive. So to the left of -1/2, the function is, there it is, concave down. To the right of -1/2, the function is moral of the story. You cannot have a point that is a relative extrema and an inflection point at the same time. Can't happen. You can try to draw one. You'll be there forever. Head will explode. It's awesome. So if we got negative 1/2 to be a relative extrema, and then we get negative 1/2 again here as a critical number, it's not going to be an inflection point. So that's a way to check yourself on your test. What happens at negative 1/2? Inflection point. So unlike our senators, you have to know what you're talking about. Where in the second derivative, it's about inflection points. There you go. Put a negative 1/2 back into the original function. Well, you can't get this. Whoa. What do you mean, like this? I don't know. I sort of like this problem. Yeah. Makes me happy. Calls me every week, see how I'm doing. Hey, G of X, how you doing? Rawr, rawr, rawr. What do you get when you plug in negative 1/2 into the function? Let's do a fraction here. What do you get? Negative 31/6? Now, when we go to graph this guy, we will need the decimal. Party, sketch the graph. Okay, let's combine both number lines. We only have one critical value, yet again, negative 1/2. From part C, we learned the function is always increasing. In part D, we learned to the left of negative 1/2, it's concave down, and to the right, it's concave up. So according to that chart on the left-hand side of the board, increasing concave down will be this shape. Increasing concave up will be this shape. So we're going to put these two shapes right next to each other. Is that okay? All right. Let's see if Dr. E. Beam messes this up again. Part A, again, does not directly affect the graph. Part B, we found the y-intercept at negative 5. Part C, we got nothing. No extrema. Part D, we have at negative 1/2, negative 31/6. Oh, why are they so close in value? What is that? Negative 5.1? Okay, so that's what I'm going to do. I'm going to declare this as negative 1. So that makes this negative 1/2. So it's going to be a little exaggerated there. What did we say? Negative 5 1/6? All right, so it's a little bit lower. That's your inflection point. So to the left of the inflection point, you're going to draw this shape here. To the right of your inflection point, you're going to draw the increasing concave up. Make sure you go through your y-intercept. Since we did not find the x-intercept, we don't know exactly where to cross at the x-axis. So anywhere is fine.